So, in the last 1.5 videos, I've shown what the concept behind an EM diagram is and how to read them, identifying key points of interest like max instantaneous turn rate, corner speed, max sustained turn rate, max straight line speed, and climb speed. Knowing this is all well and good, but without any graphs for aircraft, this is all meaningless. So, how do we get these EM diagrams? Well, there are two ways of going about this. First is the analytical method. This would involve constructing the flight model of the aircraft based on what we know about War Thunder's physics engine and the data mined flight model files. Then, based on the constructed flight model, we can simulate how much lift, drag, and thrust the plane would generate in any orientation, allowing us to calculate its specific excess power for any given turn rate and speed. Presumably all the data necessary to define how a plane flies should be included in the flight model files, apart from some of the default values that exist in the .exe file. There's been significant progress on this front since part of the Dagor engine is open source, meaning that we have somewhat of an idea of how things like engine power or wing aerodynamics work, but we still don't have a complete picture on how to fully assemble the plane using the disparate parts. So perhaps in the future we will make enough progress to the point where, based purely on the data files, we will be able to generate EM diagrams, and be able to easily assess every other flight performance metric. But at the moment, we're not quite there yet. Now the other option, which is the option I chose for these current sets of videos, is the experimental method, or basically brute force testing. Basically, the idea is, since we have a tool that can log data from localhost about the aircraft's flight state, what if we found the specific excess power at as many combinations of speed and turn rate as possible? By gathering this data, we would then be able to fill in the areas between the gathered data points using a script and interpolate a surface. Now, this is a lot easier said than done. First of all, we need to test this data with a specific set of restrictions in mind. 1. Stay at constant elevation. The more elevation change you do, the more likely changes to atmospheric and density will affect the results. I thought this wouldn't be too large of a concern, but even 300 meters of elevation change added significant amounts of variation to the results. Turning precisely at the same altitude with keyboard controls can be pretty difficult, so I tried my best to limit myself to only doing horizontal turns within plus or minus 100 meters. The reason I'm using keyboard controls instead of mouse aim to get this data is for the second reason. Do as few aileron and rudder inputs as possible. Rolling and yawing add a non-negligible amount of drag. So a given aircraft rolling at 500 kph would have more drag than an aircraft just flying straight. This means that for a given XY position on the graph, you could have two data points stacked on top of each other with different specific excess power values, which is not good when we want to be plotting 1 point per position. So I try to mostly use keyboard inputs to perform my turns and minimize the amount of rolling and yawing I have to do. And finally, keep the throttle at maximum power at all times. If I were to drop throttle at any point while recording data, that reduction in thrust would lower the specific excess power than I would have if I were at WEP for the same XY position, which, again, would be bad. Basically, all three of these restrictions are put in place so that we can plot specific excess power as a function of turn rate and airspeed, with one specific excess power value outputted by any given turn rate and airspeed. Based on these restrictions, there are actually only two things we can do to navigate the space on the chart. 1. Fly straight, and 2. Turn horizontally. This allows me to traverse this middle section without too many problems. For example, if I want to find the specific excess power, while turning at 550 kph, we just need to accelerate our plane to 550 kph and then turn. If we want to find the specific excess power flying in a straight line at 320 kph, we would need to bleed speed by turning and then level out. The reason why these two areas are not as easily accessible is because they lie beyond the maximum straight line speed and the maximum sustained turn rate speed, meaning that in order to achieve anything above the max straight line speed, we would have to dive to gain speed. And if we wanted to achieve anything below the max sustained turn rate speed, we would have to lower throttle or climb, both of which break our previous rules. The way to circumvent this issue is to break the rules before we begin logging the data, and only begin gathering data after we've achieved the desired speed and reinstated our restrictions. For instance, we can lower throttle to decrease speed below max sustained turn rate speed, and only begin logging once we push throttle back up. This method is pretty tedious since for each time you test, the plane will actively fight back to get into the middle area no matter what you do. So you have very limited time to log data in this area. This can be somewhat alleviated by using localhost commands like set altitude and set speed to quickly reset your state before beginning another data log, but it does mean that you need to perform multiple separate tests in order to get the full picture for the whole chart. So typically I will run 5 different tests. Test 1 starts at close to max airframe speed limit. I'll begin turning horizontally, which means my plane state will travel along this path. I'll keep turning until I stop losing speed, meaning I've reached the max sustained turn speed and cannot bleed any more speed. Then I'll level out and accelerate in a straight line until I reach the max straight line speed. And finally, I'll start alternating between turning and not turning while losing speed to fill in this middle area. This first test takes care of the bulk of the area we need to cover. Test 2 starts again close to max airframe speed. This time I'll do the alternating turning and not turning again to try and fill in this area. Though keep in mind that even while not turning I bleed speed, so I need to alternate quickly between the two before I end up back in the middle area. Test 3 again starts at max airframe speed, but this time I'll just fly in a straight line and decelerate to fill in this bottom line. Test 4 instead starts just above stall speed, where I'll try to maintain altitude while turning as much as possible to fill out this edge. And finally for test 5, we'll start again just above stall speed and fly straight to fill out this bottom edge. If I feel like this middle area should also be filled out, I can run one more test to alternate turning and not turning, but for props this area is usually small enough that I feel like this is unnecessary. Now that we know how we have to perform this test, the question is, what data should we be logging using Localhost and WTRTI? The answer may seem pretty simple, just get speed, turn rate, and specific excess power. Those are the things we're trying to graph, and they're all provided by WTRTI after all, right? Well, if we were to do that, this is the result. I'm plotting specific excess power on the z-axis in a 3D plot because it's easier to visualize 3D scattered data this way. And looking at the graph, this is not what we're looking for. If we do a top-down perspective, we can see that the turn rate versus speed outline looks alright, and it is sort of what we expected. But there are a lot of problems with specific excess power. In particular, we have this massive spike here at high speeds. This is likely because War Thunder RTI uses a kind of data filtering to smooth out certain parameters, which involve calculating derivatives, like acceleration or specific excess power. The exponentially weighted moving average filter that they use smooths the data, but because of the way it's implemented, it excessively trims peaks and troughs, and also introduces a rightward shift to the data. This filtering delay is also the reason why we get this weird looping effect, where it looks like there's a top and bottom surface when we're looking at it from the side. We would expect the data to fall on just one surface, since the way we gathered our data, we limited all of our confounding variables, so specific excess power should just be a function of turn and speed, nothing else. Another thing to note is that if we zoom in close to the data, you'll notice this banding effect. This is because of the low precision of the data being used. In War Thunder RTI, the default IAS and TAS parameters are stuck at precision of 0 decimal points, meaning that the data, when plotted, is quantized into specific energies that the data will snap to when War Thunder RTI rounds the data up or down. This error also propagates into the turn rate and specific excess power values, since both of these are calculated using these airspeed values. So, how do we fix this? We need to do 3 things. First, collect only direct localhost data. War Thunder RTI will collect data from localhost, and some of it is presented immediately as parameters, but a lot of these parameters are also calculated and filtered, which means there's a high chance that it's unusable. Second, gather high precision data. Of the localhosts, we should try to choose outputs that have higher precision than others. For some reason, War Thunder RTI also likes to truncate some variables' decimal points and make them less precise, such as that for the load factor chopping off the hundredths place. So we need to make sure that we get as high of precision as possible. Thirdly, we need to calculate every parameter we want ourselves. Because we aren't relying on War Thunder RTI to calculate these values, we need to basically start from scratch and do these calculations on our own. To gather the data from localhost outputs only, we can cross-check which variables War Thunder RTI hasn't filtered by just going to the localhost website and looking how they compare to the War Thunder RTI. We can see that the variables like IAS and TAS have not been messed with and just naturally have a low precision. Specific excess power and turn rate don't show up on localhost, so they must be calculated. For variables like load factor, which goes by NY in localhost, we can see that the only change is a loss of the hundredths place digit. We can remedy this by making our own custom parameter. To do so, we can press F2 from our main window to open the state menu while in a test flight, which will show all the numbers War Thunder RTI is keeping track of, both from localhost and the ones it's calculating and filtering. We can see here that the NY parameter has its full precision while in the state menu. We can then hit this plus sign to add a new parameter, right click and then select new to add our own new custom parameter, and then from this menu give it a name, specify the state key, which is the name that's shown on the state menu, and make sure to select the number of decimal points you want. Increasing the precision here won't add more precision that wasn't already in the original localhost data, but it will stop WTRTI from truncating off some decimal points. We can then hit OK, then double click it so that it shows up on our main window as being actively tracked. This remedies some of our issues with precision, but the main source of our lack of precision was from IAS and TAS, which have no decimal places, even in localhost. Now, in the previous version of WTRTI from around 6 months ago, there used to be a lot more precision, up to 6 digits past the decimal point. But back then, when I was testing things, I noticed that the WTRTI speed output and the in-game speed output would not match up, especially on VTOL planes. What I had found was that the speed value that WTRTI was using had been a different parameter than IAS or TAS given by localhost, but instead a parameter simply referred to as speed in localhost, which, as it turns out, shows the amount of airspeed the plane is experiencing along the plane's nose direction, or the plane's local x-axis. This is especially apparent when climbing while VTOLing, since you climb vertically and so you experience no velocity in the forward or backwards direction. While this effect is most apparent in VTOLing planes, it still introduces a non-negligible amount of error for any plane pulling any amount of AOA. I brought this up to the WTRTI developer, and so he addressed this issue by switching over to a less precise, but more accurate IAS and TAS output from localhost, starting version 2.3 and up. Any data tested from versions before WTRTI 2.3 will thus likely have an error in their speed values unless they explicitly accounted for this. Now, the high precision of the nose airspeed isn't useful to us unless we find the absolute speed from it. Luckily, with a bit of trigonometry, we can see that the angle that the nose would be off from the actual velocity vector would be by the angle of attack and angle of slip. So by simply dividing by the cosine of these two, we can find the full airspeed magnitude with high precision. This might lead to some problems if you're pulling high amounts of angle of attack, but since most planes aren't going to be pulling more than like 40 degrees, this should be fine for most dogfighting scenarios. Now, this nose airspeed is actually indicated airspeed, but if we want to calculate something like specific excess power, we need true airspeed. To find true airspeed from indicated airspeed, what we could do is find the ratio between localhost's TAS and IAS, and then multiply by that. But this would reintroduce the low precision issue back into our data. A more exact way of calculating true airspeed from indicated airspeed would be to find the air density and calculate how much this affects our airspeed. At sea level, TAS and IAS are basically the same, but the higher you go, the lower the air density becomes, leading to IAS becoming much lower than TAS. In Gaijin's physics engine, air density is determined by altitude, sea level pressure, and sea level temperature, both of which depend on the map. However, this is the equation for calculating TAS from IAS, where sigma is the air density ratio, the ratio between the air density at the current altitude and sea level. And because the way that Gaijin calculates this ratio does not depend on the particular settings of the map and only depends on altitude, we can just find sigma by logging altitude and not needing to account for the details on the map we're on. The way that they calculate it is using this weird quartic function, but it works, so I'm not going to question it. And as a sanity check, we can plot that our calculated TAS and IAS are close to the ones output by localhost, meaning that our method is accurate. Now that we have TAS, we can calculate specific excess power using the equation from the previous video. Here, we do need the derivative of velocity, or acceleration. We could use WTRTI's output for this, but the value is not a localhost output, and it also has the same filtering issues, so it's best just to calculate this using the velocity output we have. For the derivative of height term, we could take the derivative of the altitude ourselves, but there's already a more precise parameter output by localhost called vario, meters per second, that already does this for us, so we can just log that value directly using another user parameter. And so we have our more precise, calculated specific excess power. Comparing it to what we had before, we can see that it's a lot messier, but it also preserves more detail and is a lot more responsive to changes. Also, it gets rid of this massive spike. Now to calculate turn rate. This is the equation for turn rate in the horizontal, and is the load factor, which we again need to make a custom parameter for to get the max precision. There's not much else to say in terms of the calculation, but one thing to note is that there can sometimes be load factors below 1, which would make the term under the square root negative, which is not what we want. So to remedy this, I've decided to lock the minimum load factor to 1, and any values below that will just have to be set to 1. This is also how War Thunder RTI calculates it, and as another sanity check, we can compare our calculated and War Thunder RTI values to see that they line up almost exactly. Now that we know how to get from localhost parameters to high precision speed, turn rate, and specific excess power, here are the final list of variables logged in order to perform these calculations. These user variables are speed, vario meters per second, and ny in the state menu. I wrote a Python script to parse this data, run all the calculations I just mentioned, and graph it again. And here is the result. You can see here that while the data isn't perfectly aligned, it's much better and much cleaner, and you can make out a distinct surface made by the scatter data. Now we need a way to smooth it over into a curve fit. I tried a variety of two-dimensional polynomial surface functions, and what I landed on for now was an altered version of the 6th order polynomial. I made a few changes to this full 6th order polynomial in order to account for a few details. The first change I made to the hexic function was to remove all first order y terms. This is because at a given speed, you should have the highest specific excess power when not turning, and any elevator input, whether negative or positive, should cause a smooth increase in drag, and so a smooth decrease in excess power. This would mean that looking at a sideways slice at a given speed, the slope at turn rate 0 should be 0, and this point should be a maximum. In essence, the partial derivative of the curve fit function with respect to y should be 0 when y is equal to 0. We can see that when we take the partial derivative with respect to y from the hexic function, the only term that remains at y is equal to 0 is when y has a first order. So we can basically remove all of these terms by setting the coefficients to 0. Secondly, I removed all terms of x or y with orders 3 or 5 to remove any odd function behavior. Odd order polynomial functions will always result in functions leaving in the opposite direction that it came from, but with our graphs we want it so that our curves always curve downwards. Now here's the 3D plot with the surface and contours. And here's the 3D plot projected onto a 2D plot that we are familiar with from the previous video. You can see that the first set of alterations we made to the hexic function have made the contours perpendicular to the x-axis. This fixes an error in the original contours shown on the EM diagrams from the previous two videos, and overall, I think this EM diagram turned out pretty good. Now, there are some obvious flaws with the methods that I've used, so that means that this isn't perfect. For one, it is impossible to not roll or yaw at all or to stay at the exact same altitude when gathering data, which means that there's going to be some messiness in terms of how specific excess power is calculated. Secondly, my laptop likes to stutter a lot when running War Thunder RTI, which is why I turn the OSD off and log the bare minimum number of parameters necessary. I don't have a gaming laptop or a desktop setup, so the memory of my computer is very limited, and sometimes this results in my game or laptop crashing, and when that doesn't happen, it just stutters a lot, and this can create weird jump discontinuity artifacts that add to the messiness of the data. And also, because of the fact that I can't go past the max airframe speed to gather this data, there is this kind of gray area where I haven't been able to gather the data that is still technically accessible in flight. This method of testing is also a lot more difficult to do with planes with high thrust. For example, top-tier jets usually have a max speed above Mach, so it becomes impossible to fill out this graph because past a certain speed, you can't turn to bleed speed effectively because you G-lock too quickly. In order for us to gather data on low speeds, we would have to either drop throttle or pop air brakes, both of which would break the restrictions we set initially. On the calculation end of things, the equations that War Thunder RTI and we used for turn rate only really applies to turns performed horizontally at the same altitude with no speed gain or loss, which isn't the case for a lot of the turning that we've done to gather this data. Also, a lot of the turning that you'll do in a dogfight will be vertical, so this isn't the most accurate way of gathering turn rate data. On top of that, by setting the minimum load factor to 1, this leads to some weird banding effects that happens near the x-axis. Also, the hexic curve fit doesn't exactly fit the data. In the regions that we care about, it's fairly good, but in the middle areas you can see that it can seem a bit wibbly-wobbly when you'd expect it to be more of a single concave curve. Overall, because this method is experimental, it is inherently messy and inaccurate to a degree. It would be silly to think that we would be able to approximate a flight model using a simple polynomial fit, considering that the actual flight model of a plane is an asymmetrical summation of many parts, all of which behave non-linearly. But for our purposes, it is good enough, and it allows us to determine the key points of interest in our aircraft's flight profile. It will also allow us to compare relative aircraft performance and regions of advantage once we generate this graph for 2 different aircraft. That will then inform in what manner we should try to start and maneuver in the dogfight. This video is getting much too long though, so I'll save that for the next video. I know this was very information dense, and also doesn't have a lot of immediate in-game application, but I wanted this to be 100% transparent in the process by which I arrived to these plots. I tried to be as concise as possible, but it's understandable that this isn't the most interesting thing to someone who's watching. I just wanted to document my process here and not leave any questions unanswered. Also, for this video I only shared the stuff that worked. There was a lot of tweaking and testing and laptop crashing and retesting and debugging that happened behind the scenes. Like, this is basically what I did for like a week straight. If you want, I can share the code that I used to run this, though it's not annotated and also not made with the general user in mind, so keep that in mind. I'm out of breath, so I'll see you guys in the next video where we'll talk about something actually applicable in game.